Welcome back. We have 5.4 enthalpies of reaction. So we just saw in 5.3 what enthalpy was, delta H. And because we have a reaction, we're going to be looking at a chemical change. Okay, so chemical reactions. So learning objective, represent a chemical or physical transformation with energy diagrams. So we got to learn how to write what's called an energy diagram. We also call these enthalpy diagrams. As you see down at the bottom, oops, don't know where that triangle's there. A physical or chemical process can be described with an energy diagram to show is it endothermic or is it exothermic. So first, what do we mean by enthalpy of reactions? So for a reaction, a enthalpy change, delta H, that accompanies a reaction is called enthalpy of reaction, or you can even call it heat of reaction, because remember, why can we say enthalpy or heat? Well, if you have constant pressure, both terms go hand in hand. We have an abbreviation for it. It's called delta H reaction, and you write the little word reaction like it's a subscript. So next is something called a thermochemical equation. So what a thermochemical equation is you have a balanced equation with states of matters, coefficients, okay, all that good stuff. But then at the very end of that equation, and it has to be at the end of it, I mean, you can give it a little bit of space, but it's got to be on the same line. Then you have the delta H value listed right at the end. Now notice what this delta H value says. One, it's negative, which means the reaction lost heat, lost entropy, which means this is exothermic. Okay? Next, very key, very important, make sure you listen. This value depends on the balanced equation. It depends on the moles of the reactants and products. So this value right here, as long as you have these moles, this value is still negative 483. So what happens if you change the moles? That means the values of delta H are going to change. And I'm going to go into this in really good detail in 5.6. But let's say this equation where we took the coefficients and we divided it by 2. We took half. So we said we took H2 divided by 2. We have a half of oxygen, and then we have 1 water. What you're going to see is that your delta H also gets divided by 2. Okay, so these thermochemical equations, they depend on the moles. Next, if the states of matters change, like if you take that water and go water as a liquid versus water as a gas, that value of delta H is going to change too. So you're going to see an example coming up in this video where you're going to watch Fairbraw, and he's going to go over and explain that. What happens if I take that equation and go from a liquid to a gas? Okay, so I'm going to make a note right here. Watch Fairbraw's video. Okay, so this 483, because it's negative, it tells us that the heat, the energy was released to the surroundings when I formed the water. And because delta H is negative, the reaction is exothermic. And we know that, which means our Q is negative 2. So if we actually had to solve for W or delta E, well, then we know our Q is also negative 483.6. Okay? The other part that I always like about these type of problems is I get to use stoichiometry. Stoichiometry is coming back, okay? So you're going to see on this next page, so get a calculator now. Might as well get it because it's coming on the next page. I'm going to show you how these thermochemical equations where we use moles and the delta H in the stoich. So enthalpy diagrams, as you see in the learning objective above, AP expects you to know how to draw an energy diagram. Enthalpy diagram also, because we're using delta H, okay? It's used to represent the delta change, the delta H change associated with the reaction. Now, this was your equation above. Actually, I'll write it over here so I have more room. H2 gas, O2 gas, and then I had 2 waters. Okay, so let me make sure I wrote my equation correctly. So I had 2H2, and then I had 1 oxygen and then 2 waters. Okay, now how to write an enthalpy diagram. First thing is, okay, you're going to draw 2 lines. Okay, so as you see right here, I'm going to draw 1 line right there, and I draw 1 line right there. Next, you need to focus now on the balanced equation. Okay, and what I mean by that is you have to remember that delta H is final minus initial. Okay, we have to figure out which side. So here's the question we're going to try to answer. Which side has the higher or lower entropy? That's the question we have to answer. Okay, now I'm going to do my notes over here. If delta H is final minus initial, because it's the change in enthalpy, and all I know is that this answer was 483.6. Okay, if my answer was negative, okay, these 2 values right here, one of these 2 values had to be bigger. Which value was bigger to make that answer negative? Okay, well, we're making a big assumption. We're assuming that F and the initial, the final and initial, were both positive values. We're assuming that they were both positive values. Okay, I can have negative values if I want. We've seen that with Q and W. So let's assume that this is a positive value minus a positive value. And I got a negative 483.6. Okay, which value has to be bigger to have a negative number? Well, a number minus a number became negative. That means my initial value had to be a bigger value. And that means my final value had to be a lower value to get this negative value. So if it's final minus initial, and initial were the bigger enthalpies, the bigger value, that means my initial were my reactants. Okay? That means the lower, because it's final are the products. So with students, it's not drawing the diagram, that's the hard part. It's answering this question. Which side has higher or lower enthalpy? Because now that I know the bigger value was the initial values, the bigger value was the reactants, then I list the reactants on top. So you listed exactly the way the balance equation shows. 2H2 gas plus O2 gas, that always goes on top. The lower enthalpy always goes on the bottom. So because my lower enthalpy was my products, then I'm going to put my 2 products. Okay, seems not difficult once you figure out who is who. The next thing is, okay, the arrow. Okay, the arrow always goes reactant to product. So if my reactants were on top, my products are on the bottom, I need to make sure that I draw my arrow going down. And then after I figure out where my arrow is going, always reactant to product, okay? And then I list the delta H value next to the arrow. Okay? And that's pretty much it, enthalpy diagram. We're going to draw one with the practice problem that's on this next page, okay? Another little side note, which I'm going to fix it in my notes, is make sure that that arrow is touching from line to line, okay? You want to make sure that there's no space in between it, okay? All right, well, as I told you, get a calculator. Here we go. How do we use stoic when it comes to moles? Oops, moles versus delta H. Okay, well, as I told you before, this delta H value, it depends on the moles in that balanced equation, where if you change those moles, then you change that delta H. So we want to figure out how much heat. So I'm solving for Q. Is released, ding, 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 is released. So that means I know my Q answer better be negative. When I have 4.5 grams of methane, so I'm starting with 4.5 grams of methane, and it's burned, and it told me constant pressure, which it tells me that delta H equals Q, because that's constant pressure, okay? Well, we start with the information that we know, 4.5 grams of methane. Now, where do we always go when we have grams? What's the first step? I got to go to moles, okay? Molar mass on the bottom, and we're always putting this, molar mass always equals 1 mole, okay? We don't even look at that balanced equation yet, okay? So we need the molar mass. Well, carbon, there's 1, 12.01 grams. Hydrogen, there's 4 of them, 1.01. So I got 12.01 grams. 4 times that is 4.04. And remember, when we're adding up sig figs, the least after the decimal. So this is going to be 16.05 grams. So remember, this right here equals 1 mole. So I'm going to put 16.05. Now I got rid of the grams. Well, there's one more step now. I need to get to heat, which my heat has got to be in kilojoules because my delta H is kilojoules. So I got one more step. How does the moles correlate to that delta H? Well, now this is when you look at that balanced equation at the moles. So remember, I have moles. I want to get rid of moles here, and I need to get to heat, which means I need to get to kilojoules because my kilojoules is my delta H. I'm going to insert this value, negative 890, on top. But remember, that 890 is correlated to that mole, and to that mole, oops, and to that mole, and to methane. Because methane only has 1 mole, then I put 1 mole. So the moles in that balanced equation equals the delta H value that's listed on this thermochemical equation. That is the only time you look at the balanced equation, okay? Right here, do not look, not balanced equation moles, okay? So now I just plug and chug it in. So I got 4.5 times negative 890. And then I'm going to divide by that 16.05. And it looks like 2 sig figs, so I'm going to round it. So negative 250 kilojoules. Okay? Now, before you start putting methane, remember this is energy. This is heat. Okay? There is no chemical listed when it comes to heat and delta H. Okay? So you just put negative 250 kilojoules. And we know this is correct because it said how much heat was released. So this is how much heat was released to the surroundings when you burned this methane and produced CO2 and water. Okay, which makes sense. It's combustion. It should be releasing a lot of heat. Let's try another one. Combustion of ethanol to form water and CO2, and it's constant pressure. It says it releases 555 kilojoules of heat per mole of ethanol. Write a balanced thermochemical equation. Okay, well, step number 1, we need a balanced chemical equation. And we're using the states of matter. Now, I did say combustion. What's combustion mean? It means reacts with oxygen. So I'm going to put with O2. And it did say it wants me to use water as a gas and CO2 as a gas, okay? Well, a balanced equation means you need a balanced equation, okay? And I'm actually, let me rewrite this a little bit smaller because there's a purpose coming. Because we're writing a thermochemical equation, which means I got to list something at the end of this. I need that delta H. Now it says releases 555. So that means negative 555 kilojoules per mole. The word per means over mole. Now they want you to keep this per mole. They want you to keep the coefficient to that ethanol 1. Because if you put a coefficient on here, then that means this number gets multiplied by 2. So we keep this 1. Well, let's balance it out. C, H, and O. So I have 2 carbons, 5 plus 1 hydrogens. I have 3 oxygens. Over here, I have 1, 2, and 3. Well, I need to keep this coefficient of 1. So I'm going to double my carbons. So now I have 2. My oxygens, I have 2 times 2 is 4, plus the 1, which is 5. Okay. Let's go after fixing the hydrogens. So with hydrogens, I'm going to put a 3. Now I have 6. Now if I count up my oxygens, I have 4 right here, plus the 3. So now I'm at 7. Okay. Now I only have one place to put a coefficient, because if I change these oxygen over here, I pretty much just did all this work for nothing. So I need to keep the 1 oxygen here plus something. It's got to get me to 7. Well, I need this something to be 6, but something times 2 has to be 6, which means this is going to be, oops, that's going to be a 3. And then there's my 7. Okay, so my balance equation, which all of that work that we just did, we want to make sure we clean this up. So pay close attention to the wording when it comes to that delta H. If they don't mention that per mole, then we can actually double that delta H if we had to put a 2 right there. Okay, so right here, there's my thermochemical equation. Okay, number 2, draw an enthalpy diagram. All right, well, I'm going to put it over here. I'm going to draw my 2 lines. Okay, now I have to figure out who is higher and who is lower. So if I have delta H is final minus initial. If you want to think of it as products minus reactants, that's fine too. And I know that this was a negative 555 kilojoules answer. Assuming both of these values are positive. A positive minus a positive number became a negative 555. I know my reactants were large. I had a lot of heat. On my reactant side compared to my product side was smaller. So when I draw my enthalpy diagram, the side with the larger enthalpy, the reactants, go on top. And you know, in class, we will practice more of these. I'm just showing you the first sample. My products will go on the bottom. So don't forget the coefficients, states of matters. Okay. And now I'm going to draw my arrow. My arrow always goes, as you see at the top, reactants to products. So my reactants were on top. So I'm going to draw my line going all the way down and make sure I touch it. And then I'm going to list that delta H value right next to it. Okay. All right. Part C. What is the enthalpy change, delta H, from the combustion of 15 grams of oxygen? So I know I'm going to start with 15 grams of oxygen, and I need my balance equation. First step is go grams to moles. Bye-bye grams. Hello moles. Now it's a diatomic. I don't need to see you take 16 times 2 on paper, okay? But make sure your sig figs still stay 4 sig figs, because the numbers on the periodic table, the mass numbers, most of them have 2 after the decimal. So 2 times 16 still becomes 32.00. 1 on top. Bye-bye grams. Now here comes, look at the balance equation. Okay? According to this, I have 3 moles of oxygen, and it correlates with that much enthalpy. So I'm going to put 3 moles of oxygen, and I'm going to put negative 555 kilojoules. You don't take that 555 multiplied by 3. Remember, this delta H correlates to this mole and to that mole and to this mole. Okay? So I just list the delta H, but I have to make sure I put the moles for that chemical. So we're going to take that 15 and we're going to multiply by negative 555. We're going to divide by 32 and then divide by 3 again. So we don't look at moles for sig figs. We're going to look at, you have 3 sig figs, 4 versus 3. So my answer is going to say 3. So I'm going to get negative 86.7 kilojoules of heat, which means this reaction, if I asked you, is this reaction endothermic or exo? And we know it's exo because the delta H value is negative. Okay? And that's it. So the last part of this, you're going to go to YouTube. You're going to plug this title in. If you copy this title, plug it into YouTube, fast forward it to about 15 minutes, you're going to watch Faribrow's video. He first talks about what happens if you change the states of matter. So notice right here you have the same equation. But what if you take this gas and change it into a liquid instead? Would the value stay negative 802? Would it be less than or would it be greater? So I left you some space. Take some good notes. And then you're going to do another practice problem just like what we did. I suggest you try it yourself and then go and check your answers. Okay? All right. Hopefully that was helpful. See you on the next one.